Hello everyone, thank you for signing in and watching my live stream. Welcome to Geometry. I'm Mr. Matt and this is Dr. Tot. Dr. Tot, would you like a cookie to start? Yes. This week we're going to be talking about triangle congruency in proofs. So we're going to be using geometric proofs to prove that two pairs of triangles are congruent. Remember that congruent is different than similar. Congruency means that two triangles have exactly the same side lengths and angle measures. Similarity, or if two triangles are similar to each other, means that they have the same angle measures but not the same side lengths. The side lengths are merely proportionate to each other. Notice that there's still a relationship, there's still a correspondence between the side lengths of the two triangles if they're similar, but they're not exactly the same. The difference lies in the fact that two congruent triangles are exactly duplicate copies of each other, exact copies, whereas similar triangles are like zoomed in or zoomed out versions of each other. So one can be larger than the other one or smaller, vice versa, but they do have the same angle measures, but not the same side lengths. The side lengths are proportionate, meaning that there's a common multiple that you can multiply one triangle's side length to get the corresponding side length in the other triangle. But more on that later. First, we're going to start by reviewing some properties and just some overall ideas that are going to be relevant, some vocab too, that's going to be relevant for geometric proofs with triangle congruency. And then we're going to go through the four, or remind you of the four triangle congruency postulates in geometry, and then get into some examples with geometric proofs. So let me go ahead and share my screen with you. And just a reminder, this is a live session, so the iPad is a little bit delayed, but I'll keep track of the broadcast screen. If you need me to scroll up, scroll down, just let me know. If you have questions at any point, feel free to drop them in the live chat feed, or you can put them in the comment section below and I'll respond promptly. So just some ideas and concepts, properties, etc. that are going to be relevant in geometric proofs. So the first is the reflexive property of congruence. So this says that something is always congruent to itself. That seems obvious, but in proofs you do need to be able to state a reason for each of your statements. So for example, this commonly comes up when we have a shape where two triangles are sharing either a side length. Let me call this A, B, C, D. Or if they're sharing an angle measure. And I'll call this A, B, well actually let me use different letters. So for example, the reflexive property here tells us that side length CA in one triangle is congruent to side length CA in the other triangle because they both share that side length. They overall make this diamond-like shape, this rhombus, but when we split them into two triangles, the two triangles share a side. So by definition, that side has to be congruent between the two triangles. Similarly, these two triangles, triangle EFI, I don't know what happened there, triangle EFI and triangle EGF, triangle EGH, share side length, share angle measure GEH. So this guy right here, notice that both the triangles have that as one of its interior angles. And so by definition, the reflexive property would tell us that angle, however you want to describe that, GEH is congruent to angle GEH. So something is always congruent to itself. That comes up a lot. You do have to explain it. If you're going to use a particular congruency postulate, you have to explicitly state how you're proving each corresponding side length that makes up that postulate or angle measure that makes up that postulate is congruent between the two triangles. And so that's a common property that comes up. Also, if we talk about something being bisected, that means that it's split into two equal parts and the resulting segments must be congruent. So in this little diagram I drew, we have triangle ABC. Notice if line segment CD, if we're told that line segment CD bisects the angle ACB, then we know that angle ACD, this guy, has to be congruent to angle BCD, that guy right there. Similarly, if we're told that something is a midpoint, if a point lies in the middle of a line segment, then the two resulting segments must be congruent. So if we describe point B as the midpoint of line segment AC, then we know that AB has to be congruent to BC. And that's just the definition of a midpoint, definition of a bisector. Also, we have congruent parts of congruent triangles are congruent. This is something that we'll touch on in more detail later. But this is basically operating in reverse. If they tell you that two triangles are congruent and ask you to prove that one line segment is equal to another, this is a way that you can work backwards, because if they tell you that the two triangles are congruent, then you know that corresponding parts, either corresponding side lengths or corresponding angle measures between the two triangles, also have to be congruent. So that is a reason that you can use in your proofs. And also I wanted to remind you that vertical angles are produced anytime two straight lines intersect. So they produce two sets of congruent angles. That doesn't mean they all have to be congruent to each other. That only occurs if they're 90-degree angles. So if you have four 90-degree angles, then they're all congruent to each other. Other than that, the opposite angles are the only ones that have to be congruent. And that would be the reason for that congruency would be definition of vertical lines. Definition of vertical angles, excuse me. If you have any questions, then please let me know. Otherwise, I wanted to just remind you of the 4 different congruency postulates for triangles. So the first, we have angle side angle. If two angles and an included side of a triangle are congruent to two angles and an included side of another triangle, then the triangles are congruent. So if we have two triangles here, if I know that this angle is congruent to that angle, this angle is congruent to this one, and the included side, so it has to be the side in the middle, that's angle side angle congruency. But you have to make sure that the side length is between the two angle measures. Otherwise, it's not the included side, and that's not angle side angle. Same thing is true for side angle side, but now we have the angle as the included portion. So if two sides and an included angle of a triangle are congruent to two sides and an included angle of another triangle, then the triangles are congruent. So this guy would look something like this. So if I said that these two side lengths are congruent, these two side lengths are congruent, and the included angle measure, that would be demonstrative of side angle side triangle congruency. Now we have a postulate that talks about a non-included side. So angle side. If two angles and a non-included side of a triangle are congruent to two angles and a non-included side of another triangle, then the triangles are congruent. So an example of this, so if I know that this angle is congruent to that angle, this angle is congruent to this angle, and this side is congruent to that side, then I have angle-side congruency postulate. I do want to note, if this was over here though, notice that that doesn't match up because the congruent side is not next to the same corresponding angle. The purple hash mark is saying that that congruent side now is adjacent to angle 1, whereas before the congruent side was adjacent to angle 2. So that would not be congruent. I just wanted to point that out. And lastly, we have side, side, side. So if three sides of a triangle are congruent to three sides of another triangle, then the triangles are congruent. So that's pretty straightforward. There's no angles involved in this one. If you know that the three side lengths of two triangles correspond to each other, such that they are all congruent to each other in the same order, or can be traced at least. You can rotate the triangles around, that's fine, but you have to be able to rotate them in such a way that you have the same order around the triangle. But if you have three sides that correspond to each other and are congruent, then you know that the two triangles are congruent. If you have any questions, then please let me know. So we're going to get into proofs today. So you are going to prove to me, given that C is the midpoint of line segment AE and line segment BD, that triangle ABC is congruent to triangle, that should have a triangle symbol there. Oops. To triangle EDC. So you're going to do that by writing out a statement, progressing towards being able to prove that the components of a particular triangle congruency postulate are all true. So if you have the statement and then you have your reason, and you're going to number your statements. Ultimately, your last statement is going to be triangle ABC is congruent to triangle EDC, and that's going to be, the reason is going to be one of the congruency postulates. So if you have information for side, 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 I'm not saying that that's particularly what you're going to use here, but I'm just saying, for example, if you have enough information from the given that you can prove side, side, side correspondence, then each of the statements has to give a reason as to why each corresponding side is congruent. So you would have to have at least 3 statements proving each one of those corresponding side pairs are congruent to each other, and then that would give you enough reasoning or deductive reasoning to prove that the one triangle is congruent to the other because of the side, side, side congruency postulate. Okay, so I'm going to give you 5 minutes. Please look at number 1, and then I'll give you the solution. I'll keep track of the time in the upper right-hand corner, and I'll update it per minute. Okay, so looking at these given statements, they say that point C right here is the midpoint of AE and BD. So AE is that entire long portion. So if C is the midpoint, that means that AC has to be congruent to CE. Also, if C is the midpoint of line segment BD, then BC has to be congruent to CD. Also, lastly, notice that angle ACB, this angle right here, and angle ECD, this angle right here, are created by the intersection of two straight lines. Those are vertical pairs, and so they have to be congruent to each other. So we have a side, we have an included angle, and we have a side. So we can prove side angle side triangle congruency. So first off, I'm going to start by saying line segment AC has to be congruent to line segment EC, and that's the definition of a midpoint. And then also, likewise, BC is congruent to DC because of the definition of a midpoint. And then we also know that angle ACB has to be congruent to angle ECD because of the definition of vertical angles. Therefore, we know that triangle ABC has to be congruent to triangle EDC because of the side angle side congruency postulate. Now, your teacher might also prefer you to list out the given information first, so then the first two statements would necessarily be C is the midpoint of line segment AE, therefore AC is congruent to EC because of the definition of a midpoint, and then go into C is the midpoint of line segment BD, and therefore BC is congruent to DC because of the definition of a midpoint. So some teachers have different preferences. In the next values, I'll do those. I'll list out the given information in the first steps. But the reasoning here is really just definitional. We have midpoints and vertical angles. If you have any questions, then please let me know. Otherwise, let's look at number 2. I'm going to give you 5 minutes, and then we'll go through the answer. Okay, so if we look at the statement and reason chart, if we plot one out. So in the given information, they tell us that the angle of angle ABD, which is this angle right here, is congruent to angle CDB. That's this angle right here. Then they also tell us that side length AB is congruent to side length CD. And then also notice that they share side length BD. So we can say that angle ABD is congruent to angle CDB because of the given information. So that gives us an angle. We can also say that side length AB is congruent to side length CD because of given. That was also given information. And we can say that side length BD is congruent to side length BD because they both share that side length. And that's because, or due to the reflexive property of congruence. So we have an angle, we have a side, and we have a side. The angle is an included angle. So we know now that triangle ABD is congruent to triangle CDB because of side angle side congruency postulate. If you have any questions, then please let me know. Otherwise, you have 5 minutes. Please look at number 3. Okay, so the given information, notice that this symbol right here means parallel. So this AB, oops, that's not what I wanted to do. AB is parallel to ED. So these little arrow marks or these two parallel lines, these two vertical lines next to each other, those both indicate that a pair of lines are parallel to each other. So if AB is parallel to ED, then basically what that can be used to say is that you have a transversal. In either respect, if these two are parallel, you can think of it either as this guy right here continuing, or you can think of it as this. It really both are true, and they're true for the same reason. But let me actually back this out and let me extend these lines. So if I have these two lines and then this transversal that goes through, this tells me that now I have opposite interior angles here. Right, so I can say that those two pairs of angles are corresponding to each other and must be congruent because there's a transversal intersecting parallel lines. So let me back this out of all the red out of here. And so the first statement, they can say just the given that line segment AB is parallel to line segment ED, and that's given. We can use that to say that angle ABE is congruent to angle DEB because of the definition of alternate interior angles. For 3, they say that EB, line segment EB, bisects line segment AD. So if EB bisects AD, that means that AC has to be congruent to CD. And that's the definition of a bisector. So far we have two sets of congruent angles and two sets of congruent sides. We can also notice that these are vertical pairs here. So we can say that these two angles have to be congruent. So we can say angle ACB is congruent to angle DCE. And that's the definition of vertical angles. And therefore, we have angle side angle congruency postulate. So we can say that triangle ABC is congruent to triangle DEC because of angle side angle triangle congruence. Okay, so I'm looking at the time and we don't have enough to go through a full other example. So I'm going to call it here for today's session. However, on Wednesday, we'll get right back into this and we'll have many more examples. I'll go a little bit faster through the intro. I just wanted to make sure everybody was on the same page with the properties. But if this was helpful, please like, favorite, and subscribe to my channel. I'm Mr. Matt, and this is Dr. Todd. Dr. Todd, do you want to say goodbye to everybody? I have to bribe him with a cookie to do this, but come on. Do you want to say goodbye? Come on, you want a cookie? You got to say goodbye to everybody. Come on. Come on. Come on, you got to say goodbye. You don't want to? Come on, you want a cookie? It's your job. Come on. Come on, go up. You got to say goodbye. Come on, say bye. You have to say bye to them. Okay, just give me the cookie. Thank you guys very much for watching. I'll see you all on Wednesday.